In this video, we'll develop a second-order differential equation which models the classic mass on a spring physical system. Here I have a mass of m kilograms attached to a spring, and that's attached to some sturdy base. If I give that mass some initial position and some initial velocity, it'll want to move about according to the laws of physics and potentially oscillate for a long time or move quickly towards its equilibrium point where x is equal to 0 and the mass is at rest. We're going to let x of t represent the position of the mass on the x-axis here after t seconds. And our job is to come up with a formula for x of t. To do so, we're going to use the basic laws of physics, such as Newton's second law. Whatever forces are acting on that mass, the total sum of them should equal the mass times acceleration of the moving object. In this case, the mass is m, and the acceleration is the second derivative of the position function we're searching for, so we immediately are going to get a second-order term in our differential equation from Newton's second law, mass times acceleration. The next force that we'll model is we'll put in a force from the spring. As I move the mass away from its equilibrium point, there will be a force moving in the opposite direction, applied in the opposite direction, pulling it back as the spring gets stretched further and further out. So the larger the x value is, the further I am away from equilibrium, the more that force of the spring should be acting against the motion of the mass. So a reasonable assumption then is that the force of the spring is proportional to the distance that it's being stretched. And so I'm going to write that as k times x, where k is some constant. We're going to take k to be a positive number, in which case we better attach a minus sign to this force because it's going to want to pull the mass back to equilibrium in the opposite direction. Next, we're going to model the force of friction. And a very common assumption in these kind of situations is to assume that the force of friction is proportional to the velocity of the moving object. In this case, that means there's some constant which I'm calling beta, and we're going to take the velocity of the mass, of its rate of change, and we're going to say that it's proportional to it. And that force, again, the force of friction, will be acting in the opposite direction, so we'll attach a minus sign to it. And of course, velocity is just the first derivative of position, so we're looking at minus beta x prime, and beta here is some constant called the friction constant. Finally, there may be other external forces inputted into your system. I'll give you an example of that in a moment, but that force, that input force, will just represent as some function f of t. So for example, you may hook a wheel up to your spring and let that wheel turn around and have a little arm that hooks up to the spring. And as the mass does its oscillation according to the spring, you're also going to rotate this around and input into the mass an extra oscillating force. So that input force, the f of t that we might be using in this particular example, might be some sinusoidal input function, like f of t is a times the sine of bt, and a would represent the amplitude of that force, and the b would represent the angular frequency of the force. Now let's develop our model. We have all the ingredients. Newton's second law says the total sum of forces should be the force of the spring plus the force of friction plus any extra input forces that we have in our system. In this case, the force of the total forces is given by mass times acceleration, so we get our second order term, m times x double prime. The force of the spring is proportional to position, so minus kx. The force of friction is proportional to velocity, so minus beta x prime. And then we have this extra external forces that we may be adding in, which we're calling f of t. And right now we have a differential equation. It's second order because of this second order term here, and we're finding the function x that satisfies this differential equation. If I move some of the terms to the right or left hand side, it's going to look a little more familiar to us. Here's our second order term plus now the first order term and plus the zero order term. On the right hand side we get some input force, and what we're seeing here is a second order linear differential equation with constant coefficients. On the right hand side, if it's not zero, it will be a non-homogeneous differential equation. Let's look at probably the simplest example to see whether or not this is agreeing with our expectations. Here I'm going to have no friction, and I'm going to take no external forces. So what that means mathematically is I'm going to set beta, the friction constant, to be 0, and I'm going to set this input force, f of t, to always be 0. My differential equation will be very simple then. It will be m times x double prime plus k times x is equal to 0. I'm going to divide that equation by m just to make the coefficient here 1. And when I do that, I have a coefficient here of k over m in front of the degree or the order 0 term. Just to make it more convenient, I'm going to let the Greek letter omega be the square root of that coefficient. This is some real number. K and m are positive numbers, and so this is a real number here, omega. And the coefficient that I'm looking at right here, the k over m, is in fact the square of that value. So my differential equation looks a little nicer if I write omega squared for that coefficient now. If we write that in operator notation, we're saying d squared, two derivatives, plus omega squared times my function, applied to this function x, should get 0. So we're looking for functions x that are annihilated by d squared plus omega squared. The roots of the corresponding auxiliary equation are easy to find now. If you set it equal to 0 and you solve for the roots, you'll see that the roots are minus omega squared and the square root of that, and don't forget plus or minus. Now, omega is a real number. Its square, therefore, is something positive, and therefore, under the radical, because of this minus sign, we really are seeing two imaginary roots. They are plus or minus I times omega. And this tells us that we should have trigonometric solutions, sinusoidal solutions. And in fact, the general solution is x equal to c1 times cosine omega t plus c2 sine omega t. The number omega that we saw as the ratio of the spring coefficient to the mass is determining the angular frequency of this sinusoidal solution here. And if you choose specific initial conditions, initial position, and initial values, initial velocity, you can find C1 and C2, and you will see after plotting it that you'll have some sort of sinusoidal signal. That should make sense if I have a mass on a spring with no friction and no extra forces, and I let it rip. I give it some initial position, I give it some initial velocity, it will want to oscillate backwards and forwards forever. There is nothing stopping it, there's no friction to dampen its position, and therefore we will see something purely sinusoidal as a solution.